Okay, so again, your test is going to be on Monday. I'll send out a reminder on Sunday that help session is Monday morning, 7:15. Make sure you bring your calculator and look over your quiz, look over your reviews, do additional problems with derivative graphs, optimization, and function graph, where like page 1, 2, and page 8, those types of problems. But hopefully having some additional days, you guys will feel really good about being ready for Monday's test. So the calendar is on the second page of your packet. So I printed this out before I made the change to the schedule. So today we're going to go over first two sections of logs and differentials, derivative units. So we're doing natural log derivatives and log differentiation. And then we'll take the test on Monday, and then we'll continue with the sections from the tests. Yeah. Okay. Okay, so just to kind of give you an idea here, we're going to get through this unit without taking a quiz. So we're just going to take a test, but it's just going to be a couple of sections here. There's going to be quite a few derivative rules that we have to kind of go through. So we'll get through everything by Thursday, and we'll have 4 days to do test review, and then the test that second week of November, that week of that election and that election week. And then we're going to start our trig unit. And there's only 3 weeks in November, so we're going to start that trig unit. But no test on the trig unit until after Thanksgiving break. So after Thanksgiving break, we'll take a trig derivative quiz, and then we'll start preparing for, we'll have another couple of sections to do in trig unit, and then we'll take that test that last week. So that finals week, I mean, there is no finals, but that final week, it'll be that Monday. Okay? That Monday, I think like the 11th or something like that of December. Okay, so we're nearing the end here. We covered majority of the major content, but we're just kind of going back and looking at previous material from different functions perspective. So from a log perspective, from exponential perspective, and then also from trig perspective. Okay, so page 1. Okay. Okay, I'm gonna have you guys copy down a couple of things here. Log unit was one of the final units that we did from Excel pre-calc, so hopefully we still remember a good chunk of it. This is what a natural log of x graph looks like. Natural log, well, all log graphs will kind of have this form, but natural log has the cleanest properties amongst all the log functions, so that's why we kind of treat natural log as a kind of like a parent function, because it just has these really clean and easy relationships, also from a derivative standpoint as well. So E is an irrational number close to 3. You know that pi is 3.14, and E is a little bit less than 3, so it's around 2.7. So, okay, this is a really helpful graph to memorize. it doesn't seem like there's a lot going on here, but there's a lot of helpful information. With a natural log graph, there's three things that you can hope to. Three things I want to point out. One is that there's a vertical asymptote at x equals 0. The second is that there's an order pair at 1, 0. And third, there's an order pair at e comma 1. And that is the reason why this is so helpful, is because we can find out values. These values of natural logs that are also important properties, and important properties are a lot easier to memorize if we have a picture in mind. So natural log of 0, in this case, is undefined, and that's also a property of natural log. Natural log of 1 is what? 0. That's an important property that if you have the graph, if you visualize the graph in front of you, then this property kind of just comes from the graph. And natural log of e is equal to what? Well, e is 2.7, but what's natural log of e? Natural log of e is just the y value, right? The y value is 1, right? We're just pulling order pairs, right? Order pairs. Right. Natural log of 1 is 0. Natural log of e is 1. So these are all really helpful, important properties. But if you can see it from a graph perspective, that's also really helpful as well. So a natural log graph has a domain from 0 to infinity. That means doesn't exist to the left of 0. I can't take a natural log of a negative value. Okay, well, also it doesn't. You can see that's also true because it doesn't exist in the negative region. The range, though, is all real numbers. The graph extends from negative infinity all the way to positive infinity. It looks like there's a horizontal asymptote here, but the graph is it's rising at a very slow rate. So it is moving its way up to positive infinity. It's just going to take a long time to get there. So some graph characteristics is that my graph within its, if it exists, that it's always going to be continuous, it's always increasing, and it's always concave down. And we see that concave down shape with this graph. All right, so if I want to sketch a graph of natural log of x minus 3, understand that this x minus 3 is really just taking my natural log graph and it's just shifting it to the right 3 units. And then basically the vertical asymptote is what's moving, right? So natural log of x would just be x-intercept vertical asymptote at 0. Natural log of x minus 3 means that there's a vertical asymptote at x equals 3. And if I can draw my vertical asymptote, then it's a lot easier to build my graph because I know my graph is just going to be to the right of that asymptote. Example 2, draw the function, and the function is referring to natural log of x. So here's natural log of x, right? X. Some properties here. Limit as x approaches 0 from the right. That means we pick a point to the right of 0, and then we follow the graph left. And where's the y value going to? Negative. Okay. Limit as x approaches 0 from the left side of 0. That means I have to pick a point starting on the left side of 0. Do I have anything here? No, right? So I can't move towards 0 on the left side if I don't have any graph here. So in this case, the graph doesn't exist, so I can't find the limit. Limit as x approaches 0. So if I want to find the full limit, I need to pick 2 points on either side of my target. But first, there's no real number here, and second, there's nothing on either side. I can't move towards a certain point without there being a graph there, so it doesn't exist. Limit as x approaches infinity. That means I'm going to follow the graph to the right. If I follow the graph to the right, where's the y value headed? Going up, right? The y value is headed up to positive infinity. Okay, so these are important and nice properties to know, and some of these are just coming from your order pair, right? Natural log of 1 is 0, natural log of e is 1. And these are product and quotient and power property that we've seen in the past, meaning that this is product property. If I have if I have natural log of a times b, I can expand that out into natural log of a plus natural log of b. Likewise, I can take this and I can condense it to natural log of a times b. If I have natural log of a over b, I can expand that into natural log of a minus natural log of b. So this is quotient property. Likewise, I can take this, I can condense it into natural log of a over b. Finally, power property. This one I find to be the most useful. We're going to use this a lot here. Power property says that if I have an exponent within a natural log function, I can drag that number in front, or I can put it back up. Right? Normally we can't do that, right? Normally I can't just take an exponent and just move it down or move it back up. I'm changing the overall value. But the nice thing about natural log is it allows that exponent to come down without changing the overall value. We're not taking a derivative, but the reason why this is helpful is because sometimes being able to move an exponent down allows us to have more options operation-wise. Sometimes it's difficult to work with exponents. If I can bring it down, we can have a lot more options and flexibility in terms of how we want to work with a problem. So this power property is really nice. There is one thing that we cannot do. If I have natural log of a plus b, I cannot do this. I cannot say natural log of a plus natural log of b. I know that this is going to feel like it works because why not distribute if I see a parentheses? But a plus b is not outside of natural log. I can do it if it was like, let's say if it was x times a plus b. These are completely independent of each other. I can distribute this through and be fine, right? But a plus b is not separate from natural log. This is inside the function. So if it's inside the function, I can't do anything with this. So if I see natural log of a plus b, I gotta leave it. Okay, I cannot expand. I can expand it if it's in this form, right? Natural log of a times b is natural log of a plus b. Natural log of a plus natural log of b. So we don't want to get these confused. So this we cannot do. Okay, so expansion means we're going to take what's inside the natural log expression, and we're going to turn this into an addition, subtraction, or multiplication problem without the exponent. So natural log of 3e squared, I can use product property. I can treat 3 as my a. I can treat e squared as my b, and I can just expand out to get that 3e squared into break it up into smaller parts. Can't do anything here. Natural log of 3, that's just some decimal value. We'll leave that alone. But natural log of e squared, there's another property we can do. What's that? Power property. We can bring that exponent down. Again, this is not derivative, okay? I know it feels like, oh, derivative, I just bring the exponent down and subtract 1, right? But this is not, this is just a property within natural log. So I can bring that 2 down in front. There's one more thing, yeah.
Why couldn't you start off like doing the power property?
Power property. That's a good question. The reason why is because this e squared doesn't see the 3. So the e squared, the natural log of e squared needs to be separated before we can do the power property. Now, if it was this, if it was natural log of 3e parentheses squared, then yeah, then that 2 can come down because the 3 is inside. But okay. Here the squared is only impacting the e, so it can't come down in front. Okay. All right, so now natural log of 3 plus 2 natural log of e. There's one more thing we can do to clean this up. What's natural log of e? 1. So natural log of, yeah, right here, natural log of e is 1. So we can't do anything more. This is just some decimal value, but this is an exact value form. Okay, condensing is where we're taking something that is all separated, and we're going to merge it all into one log or one natural log expression. So let's look at example 2, or next page, sorry, example 4. So it says condense 2 natural log of x minus natural log of x plus 1 minus natural log of x minus 1. So there's a big bracket here. So that 2 we're going to handle last. We're going to handle what's inside the right of, or inside the bracket first. Now here's a quick way to help with the condensing process is that, well, you know that ultimately you're trying to get everything under one natural log expression, right? You know that's the goal. So where do all the pieces go? Easy way to know where the pieces that we're working with, we should have to find a home for the x plus 1, and the x minus 1. And we're trying to condense it into one log expression. An easy way to quickly get into condensed form is look to see, is your expression part of a positive or a negative natural log? If your variable or if your expression is part of a positive natural log, it's going to go with the numerator. If your expression is part of a negative natural log, it goes in the denominator, and that's it. You just place your numerator and denominator based off of the sign that you see in front. So this x is going to go where? Up top. This x plus 1 is going to go where? Bottom. This x minus 1 is going to go where? Bottom, because that minus in the front. That's it. Okay. There's one more thing here. There's that 2 that's sitting out in front. If I want to condense, I'm trying to get everything up to the right of my natural log expression. So any idea where I can put that 2? Okay, well, this is a power property here. If I have n times natural log of a, where can I put that n? Exponent. So I can push that 2 all the way up. And I can also just do a little bit more cleanup and just merge that together. Okay, so that was just a bit of a review for properties with logs and with natural log. And also, all these properties also works for any logs of any basis. So if it's base 2 or base 3 or base 5, all these properties are still true. Okay, so here is our derivative rule for natural log. This is an important derivative rule. I'll point out the rules that are that have less chance of showing up on the AP exam. We're still responsible for the lesser rules on the quiz and test, but this is a big one here. So power rule, natural log, and exponential and trig functions, those are the major ones that you can expect to see on the AP exam. So natural log of u's derivative is just u prime over u. We take whatever is inside that natural log expression. We call that the u value, and then we do whatever it takes to find the derivative, and we put that up top, and we divide it by the original u value that we have in front of us. So if I have y equals natural log of x, then y prime is simply equal to, this is my u value. So what's u prime for x? What's x's derivative? Just x itself. What's the derivative of x? 1. So that goes up here. So u prime says just take whatever my u value is, take its derivative and divide it by what? What's my u value? X. So it's 1 over x. That's my derivative. Okay, does everybody see how we use the rule there? If my u value is x, then x's derivative is 1 divided by my u value, which is x. So this 1 over x is going to do the job of describing how the slope is behaving on this original graph. Same concept, we just have all these new slope formulas that we're going to come out with these new functions. Okay, so here, natural log of x squared minus 5, again, we got to leave it in this form, right? I cannot distribute this through and create a different problem out of this. This is as cleaned up as I can get on this side. Okay, let's jump into our derivative rule here. What's my u value? That's my u value. So my rule is simply u prime over u. Okay. What's u prime? 2x divided by, over my original u value. That's it. That's my slope formula. That's my derivative. Okay. If I want to find the slope of this graph at any point, I just plug in the x value, and whatever number I get, that is how steep this curve is at that point. Okay, so let's look at example 7. Oh, and then if we 5 and 6 hopefully didn't take much room. I do want to save this space for another example that we're going to do, example 8. But let's look at example 7. If y equals natural log of x cubed over square root of 2x cubed, find y prime. Now, the thing we have to be thinking about when we see a natural log problem or log problem is, let's always take advantage of expansion if we're able to. We would prefer not to do u prime over u at this stage, right? If I want to find the derivative of this messy expression, I got to go through quotient and chain, and we would prefer to avoid it if possible. But if I'm under a natural log expression, I have all these properties available to me, and I'm going to take advantage of these properties because if I can expand, if I can use expansion properties, then I'm able to split up my messy problem into smaller chunks, and then my derivative should be a lot easier. Even though I have more derivatives to take, each of them are going to be easier than if I'm just doing a whole one messy rule. So let's see what we can do to expand. Okay. Do we see a numerator denominator portion here? So I can use quotient property, right? Natural log of a over b can be expanded into natural log of a minus natural log of b. Okay. This one is, I mean, we can bring the 2 down, but anytime you feel like your u value feels easy enough for your derivative process, then that's when I would stop expanding. Okay. Sometimes it's not worth the effort to expand all the way if you feel like, oh, that u value doesn't look intimidating. I know I can find the derivative. But the second term, I would prefer to work a little longer with this. Okay. What can I change that radical to be? Yeah, 2x cubed raised to the 1/2. And this I would prefer to expand even further because I don't want to have to go through chain rule with u prime. Where can I put that 1/2? In front. And this is still not a derivative process. This is still cleanup because we would prefer to get to this stage so that our u value feels easy. Okay, so now we can jump into our derivative rule, right? We have u prime over u for both of our terms here. So we got to do this twice, right? These are independent terms. They're both going to have their own derivative rule. Both of them, though, we can do u prime over u. What's u prime over u for my first term? Coefficient is just going to hang out in front. But then we can do u prime over u again for my second term. And what's that going to be? I'm just going to ask you to clean up as much as you can, but I'm not going to require that you find common denominators. So you can just leave it answer in as simplified form as you can. So 6 over 2 is 3, 3 over 2. The x's can cancel out mostly, except there's an x left over in the denominator. I mean, this isn't bad. You can merge it into one fraction because it's almost a common denominator, but this is fine. Okay, we're going to revisit a lot of rules that we've seen back when we did derivative unit. So if you guys can, hopefully you didn't take all the space for 5 and 6. I'm going to call this example 8 here on the same page. Okay, find the derivative for this equation 4xy plus natural log of x squared y equals 7. We haven't seen this type of problem in a while, but what's involved here based off of how this equation looks? Implicit, yeah. You see how y's are out of place, or you see multiple y's. You know that you got to keep track of your y's. So, how many y's show? How many times do you see the y variable show up? Twice. So you're expecting 2 dy dx's when you find your derivative. Now, can you recognize what's needed here? Product rule. Okay. Now this one, we have some things that we can do before derivative, right? I mean, we can jump into derivative, but having to do u prime over u and having to go through product rule again, prefer to avoid it, right? This one we can avoid because we can use properties, right? We can use this expansion property, natural log of a, b. So anytime you see natural log and there's derivative involved, consider, okay, what can I do to make it easier? Because I do have an option to clean things up. So before my derivative, I'm going to just try to clean this up a bit. So natural log of a times b is just natural log of a plus natural log of b. Okay. This u value is not too bad, but if you want to bring that 2 down, you can as well. Actually, it could make it a little bit easier. But no derivative here, right? All we're doing is we're just making our life easier on the second term because we're able to take advantage of expansion properties. I mean, we have more derivatives to take, but they're both going to be easier. Okay, so product rule first, right? This one we can't avoid product rule. Okay, f prime g plus fg prime. I'm going to treat 4x as my f, and I'll treat y as my g. So what's f prime? That's 4. Y, no changes, or sorry, g function, no changes. Back to f. And g prime, okay, what's y's derivative? 1 dy. So when we're involving y's derivative, we've got to attach dy dx. Two natural log of x's derivative is 2 times u prime over u, right? So 2 times 1 over x, so 2 over x, right? Or 2 times 1 over x. natural log of y, okay, u prime over u, what's the derivative of y? Yeah, so 1 over y times dy dx. Equals what?
Like, original 0.
0, yeah. 7 is also being impacted by the derivative. We make it 0. Okay, so now we're just trying to clean things up here. We expected 2 dy dx's, and we did see those showing up. But now I'm just going to add and subtract in a way where I can factor the dy dx out and then move everything over to the other side. Let's factor out the dy dx. Divide both sides by the parentheses. We can leave our answer like this. That's fine. Okay, let me show you one more thing here. This is another concept. This concept is called log differentiation. So let me show you this on page 3. And now we'll just try to squeeze in 2 more examples. Okay, so example 1 and example 2. So this concept is called log differentiation. Log differentiation is simplifying non-log functions. So we gotta make sure that we do this correctly. Non-log functions using log properties to expand before differentiating. So we saw how helpful log expansion can be, right? We're able to, if we can take a log expression and split it up into easier parts, that's a nice feature to have. So the idea here is, what if a function does not have a log? Is not part of a log function. What if we introduce logs into something that has no logs? Then all of a sudden, we're going to have all these properties available to us, which we can then apply. So, but this only works if there's no logs in the problem. Okay? We don't want to introduce logs into a problem where there's already logs, because then you're adding another layer, and it's not going to make it any simpler. So we only do log differentiation when there is no logs at all showing in the equation. Okay, so that's something that I see students do, where they do log differentiation, but there's already logs in the problem. So what we're going to do is, one purpose of doing log differentiation is where there's another rule available to you, but you prefer not to go through a set of messy combination of product, quotient, and chain. Okay. So here, I mean, we could definitely solve this one, right? But this one, we got to do quotient rule and a series of chain rule. It just feels messy. It's doable, but it's messy. But what if we can do this? What if we can introduce logs into the equation? But if I introduce logs into this side, I gotta do it to both sides as well. So let's do this. Natural log of y is equal to natural log of x minus 2 squared over. So now that there's natural log with this expression, now I have all these options open to me now that wasn't open before, right? Because now I can do quotient property, I can expand all this out, I can use a power property, and I can split this up into much easier derivative rules for me to apply. So you can see that clearly there's a natural log of A over B that I can apply. So we're going to do a whole bunch of cleanup. So most of our steps is cleanup, no calculus. We're just getting this to a stage where the calculus will feel easy or easier. Okay, so natural log of A over B can be expanded into natural log of A minus natural log of B. Okay, the cleanup process continues. What can I do here to make this easier for my derivative step? Exponent down. And I can do what here? Get it raised to the 1/2 and also bring that down, right? So when you go through when you go through log properties, your log expressions should feel like they're fairly manageable. Yeah, I'm going to skip a step here, and I know that's raised to the 1/2, and I'm going to bring that 1/2 down. So everything feels easier than before. I mean, we have more things to take care of, but they're all more simple problems than what we started with. So now we can move on into our derivative step, right? We can find the derivative of each, but you see y is no longer by itself here, so we got to do a little bit of what? What happens when we see something strange with y's or something off with y's? A little bit of implicit, okay? So we got to attach our dy dx. So we are introducing implicit into the problem because now y is no longer by itself. But we just go through our derivative steps. So natural log of y, we do u prime over u. So what does this turn into? 1 over y times dy dx, yeah. And eventually we'll resolve that dy dx. We'll come back to that when we need to. Okay, so now everything is just u prime over u. No messy chain rule here. So the 2 is going to stay. That's my coefficient. What's u prime over u for my parentheses? Yep. Okay. I'm going to clean this up in a second, but basically this is our derivative, right? I want to solve for dy dx. That's my y prime, but I have to move this y over, right? So when this y comes over, dividing by a fraction is the same thing as multiplying by its reciprocal. So this y is going to come over to the right side as this. Dy dx equals y times. Do a little bit of cleanup here. The 2 and the numerator and denominator can just cancel out because these are multiplied. There's no addition and subtraction that's separating these two. Well, at least not within this fraction here. So we have our derivative, but we started with a function, so we can end in a function. So this y is only a temporary variable here. We can replace the y back in terms of the original equation, right? So you guys see that because this y is equal to this expression. So we can bring all that down. So when you go through log differentiation, your answer is going to feel really messy because you've separated everything out. But I'm not going to ask you to find a common denominator. You can just leave your answer in that form. So when that y gets replaced, this is what our answer will look like. All right. The y gets replaced with that original function. And then we just copy down the rest that we have before. So there's two different scenarios when we would like to use log differentiation. One is when we want to avoid a messy series of chain, quotient, and product rule. The second is where we have no choice but to use log differentiation because we don't have a rule available. So we have to use log differentiation to create a simpler version of a problem. So let's look at example 2. So this one, I think, is the more important one because as far as log differentiation goes, this one has a chance to show up more on the AP exam. They like to do these types of problems. So, and also you can expect to see something like this on the test as well. So let's say I have y is equal to x raised to the 2x plus 3. Okay. Now, this is not power rule because power rule will be a variable raised to a constant. We also have something called an exponential function. Exponential function is where I have a constant raised to a variable. We do have a rule for that. We'll talk about that later. But this is a variable raised to a variable expression. Do you see that? Base is variable, numerator is also a variable. We don't have a rule for this. Okay, this is not power rule, it's not exponential rule. So we have to find a way to avoid this situation. The way we can avoid it is, what if I can bring that 2x plus 3 down, then all of a sudden I don't have to deal with that exponent. So the way we can bring the exponent down is let's make this into a log expression. Then that exponent can be free to move down, just like how we saw in the previous problem. So we have to be able to recognize, oh, this is a variable raised to a variable. I don't have a rule. I have to use log differentiation. So we'll take the natural log of both sides. I'm going to put that 2x plus 3 in a set of parentheses, just because we're going to see something that we're going to need to have those parentheses in a second. Okay, so now I have a log expression. The right side has that exponent, which I can now do what with it? Bring it down. And there's no calculus, right? This is not power rule. This is a power property within logs. Okay, again, natural log of y. So just like before, we got to do a little bit of implicit on the left side. But look at the right side here. That 2x plus 3 came down. Now we have something available to us that before we aren't able to do, but there's a new rule that is appearing that we have to apply. What's that? Product rule. Yeah. So when you do log differentiation with this type of problem, you're going to have product rule show up. Okay. Okay. So natural log of y, just like before, that's u prime over u times dy dx. So just 1 over y times dy dx. Product rule, f prime g plus f g prime. Okay, let's step through our derivative here. So 2x plus 3's derivative is 2 times g. Back to f times g prime. What's natural log of x's derivative? 1 over x. Okay, bring the y over to the right side, just like before, and then replace the y back with the original equation. And there's no need to simplify your answer. However messy it looks, I'll take it. Okay, replace the y with back with what? The original. Yeah. So when you go through log differentiation, you're introducing you're introducing natural log into the problem. It's already a function, so it needs to be represented as a function. So we should be able to get everything back in terms of x. Okay, your homework is page 5, but this homework is not due until Tuesday. Okay, so Monday you're taking the test, but then your homework will be page 5. This is due Tuesday. Okay, come get your phones.
Yeah, this.
I thought I missed the review. Yeah, but we didn't do anything new on Thursday, though. We just did more practice that we did on Wednesday review. Okay. So I think you should be able to take it. You have the weekend to study. Yeah. Because I mean, you were gonna take it Monday anyways. Yeah. Right. Yeah. Well, I thought since I missed.
Like, that's why I like the teacher drawings.
So the only one I know. I just don't know. I want to call the current. Okay.
They got a lot.
Okay.
I mean, I could have played that off the video.
You have the quiz and I'm doing the quiz like this weekend, like practicing the question. I'll never do a picture of this or something. It's hard to sorry, are you is it uploading to the website? Yeah. If you have your version. Yeah.
It's never fun to make things are fun.